Hello, Assalamu alaikum. Students online, can you hear me? Can you see the screen? Okay. Today, inshallah, we're going to start our meeting number 7, where inshallah we'll talk about digital media. This is our today's topic, digital media and human-computer interaction. So inshallah today we'll discuss what is digital media, what the things we have in digital world, how the analog is converted into digital. Because the world we live in is an analog world where the things are not fixed. There is no discrete things. There is no finite things. And the computer world is called the digital world, where the things are in numbers, there is finite things. So we talk about today, inshallah, conversion from the analog world to the digital world. Noora, can you hear me clearly? Is there any disturbance in the sound? There is an echo. I think you turned on your microphone. Check your microphone, Noora. Might be you turned on your microphone. Okay, so today inshallah we talk about digital media and human-computer interaction. In introduction, the term digital media includes both tools we use to create media, such as the text, images, audio, videos, and also the idea of communicating and sharing through the internet and the web. Digital media is creating digital things and sharing the digital things in the network, in the internet. Like for example, we have this social media, right? Social media is from digital media. You have the social media like Facebook, Twitter, web apps, fine. You use the social applications like WhatsApp, messengers, where we share the digital things, digital media. That is, we share the text, we share the images, we share the video, audio over the internet. So what we share is in digital, is in digital. So nowadays we have the technologies, we have the things which can be used to share the things digitally. You can share your video on Twitter, you can share your video on YouTube, you can share your video on Facebook, your photo, your images on Facebook, you can share your audio and text messages on Facebook, on social media. This all what you are sharing is digital media. So digital media includes the contents plus the sharing and the communication. The contents, what is the image, what is the video, what is the audio, what is the text, plus the sharing of these contents and communication of this content is called the digital media. This both includes in the digital media. Technologies have developed the protection and distribution of digital media content as well as its consumption. Nowadays you see the YouTube. How many videos are there in the YouTube? Every second, every minute there is an upload to the YouTube, and there is a sharing of video and audio and videos, images. Fine. So we have the technologies now to share the content, to share the digital things, and we have the technologies to see the things, see the digital things. We can view the YouTube videos, we can see the through the internet, Facebook videos, and all digital things we can access. Whether in educational or training context or in a work-based setting, the use of audio, video, a richer and more interactive environment for educators, other presenters to express the message. Of course, audio and the video plays a big role in communication. Like I am communicating with you, you are online now. So here we have two things. We have the audio as well as the video, where I am communicating with you through the internet. So communication, whether in educational institutes like what we are using now, we are communicating digitally. Can be garbaged, copied and modified, but this is often illegal. We cannot, change the contents of once. We cannot take the contents of once and copy it or, tear it or use it illegally. So it is illegal. So what we have the privacy and the copyright properties for the contents, privacy and the copyright or IPR, property right, contents. So property right or the privacy will tell you that whether you can use these contents or you cannot use these contents. You are free to use these contents or you are not free to use these contents. So we'll start with the digital world, like how the digital world works in. First of all, we want to know that what is a digital, what is analog. The real world in digital form, how we can present it. There are two things here to represent any information in the real world is analog representation and digital representation. We live in the analog world with an infinite range of sounds, colors, touches, smells that we perceive through our sense. Analog representation that represent an equivalent to the real world aspect we're trying to capture. Like for example, a temperature is analog. Temperature, we cannot say in a fixed temperature. It is a continuous analog representation. Continuous analog representation. So we can say that there is a infinite set of numbers between two numbers. If you talk about the temperature, let's say between the temperature, we have the 20 degree to 30 degree. There is infinite set of numbers. It can be temperature can be 20.0000001. So there can be an infinite numbers from 20 to 30 if we talk about analog world. Fine. So analog thing is continuous, fine, and infinite. So the temperature, for example, is analog and can take any value within a given range. Between 20 and 30, it can take any value. So there is no fixed things. Like for example, we have 20. After 20, it is 20.5. After 20.5, it is 21.5. So the value can be either 20.5 or 21. There is no like 20.55. There is no 20.55. There is only this one. You might have seen the digital watch, the digital clock, digital meter, the digital speed meter will show you only the numbers. That is 20, 21, 22, 23. There is no point values. There is no point values. Fine. So in this case, this is what we call it as in digital things. When temperature is measured by a traditional mercury or alcoholic glass thermometer, we have the continuous analog representation like you see here. Right. Now another way to measure the temperature is by using a digital thermometer where a sensor is used to convert the temperature into the electrical voltage like you see here. Now this is a digital temperature which will show you 0.1 value only. Fine. The 0.1 value, we have the discrete values, fixed values. So at this stage, the representation analog voltage is converted into a digital representation, a numerical value, okay, which means that the values are converted into a discrete values. Like the values can be only between, like say for temperature, what is the temperature? Say like okay, 10 degree. What is the next temperature? 10.1 degree. Next temperature 10.2 degree. Next 10.3. Next 10.4, and so on. So there is a fixed numbers. It is either from 10, then 10.1, then up to 11. So there are 10 numbers from 10 to 11. There is a fixed values. So that fixed values, we call it as a discrete values. So a discrete value is something that can be counted and where continuous data is measured. One example of discrete quantity is the number of people in a room. How many people in a room? We say like, okay, there are 27 people in the room. 27 people. We don't say that there is 27.23 people in the room. That is wrong. There is 27.2 people in the room. Wrong. What is 0.2 people? 27.5. What is 0.5? Half person? Or what? Half man or what? So the discrete values which are fixed, fine, and jumps in fixed quantity. That's a discrete value. So for people, number of people in a room, peoples are counted as whole numbers, 1 person or 2 person or 3, 4, and so on. That is the discrete values. You can also see in this graph the temperature plot in discrete and in analog. So the line, the black line here, that is curving like this. Fine. This is an analog line. Fine. So there is no discrete change here. There is no fixed discrete change. No change in steps. The changes are not in steps. But if you look into this green line, it is in fixed length. You see it goes like in fixed length, like this. Let's say like this. Now you see that there is a fixed, points that is jumping. The line is jumping in fixed points. That is what is called discrete. Fine, or digital. Fine. And the line, the smooth line, the red line here, it is not in discrete, but it is in analog. As you see, this is smooth line. It is in analog. So at this point, if you talk about this smooth line, the black smooth line here, at this point we can say that it is at 4.9. Okay, but it goes down here to 4.8, let's say. Fine. Till here it is, let's say, 4.7. But the digital line, what you see, the digital line, it is 4.9. From 4.9 it is directly going to 4.7. And then from 4.7 it is going to 5. Directly to 5. But this analog line, you see that it is going down and taking up. So somewhere in between it is 4.8, 4.9, 4.910. The changes is not continuous. There is no discrete steps. So that's a analog, and when there is a changes are in fixed steps, that is the digital or discrete values. Now here we have an exercise. It says, which item in the following list are fundamentally analog and which are discrete? So now you answer me this question. What are the items here we have is analog and what are we have discrete? The amount of heat coming from a fire, is it analog or discrete? Yes, students online, the amount of heat coming from a fire, analog or discrete? It is analog, right? Why? Because we don't measure in discrete steps the amount of heat coming. The energy of a star, analog property. Pressure of atmosphere, pressure of atmosphere. Are you sure? Discrete. Okay, what about price of petrol? It is discrete. We know that price will rise in points in discrete. Okay, this is analog, this is discrete. Size of audience at a play, speed of a car, analog. So the first is analog. Pressure of atmosphere is also analog. Digital. This is analog. So I think you got what is analog and what is digital. Okay, the next is representation. That's all about analog and digital we had. The next we are going to talk about representation. Representation plays a central role in facilitating communication by establishing a relationship between some symbol of perceptual form, and some meaning to that symbol. Representation is about representing something or telling something, right? Telling something. For example, a flag of a country says a flag will show which country. Or you can say, what is this? If I ask you, what is this? Yes, students online. If I ask you, what is this? This is a number 5. So if someone asks me, what is my marks? I just say this. It means that I am presenting the information as your marks is 5. Okay. Now what is this? This is V, letter V, or it can be number 5 in Roman. Okay. This one, it can be letter X or multiply or no mark. Fine. So we see that there are some symbols that has some meaning, is used to represent something, to present something, to present something. For example, crosses on church, crescent on mosque indicate places of worship and are intended to be seen. It means when we see that there is a cross in the church, the crescent moon on the mosque, we'll say that this is are the places, will represent that these are the places for prayer. Bleeps at pedestrian crossing indicates the lights are green and intended to be here. So we have some representation to present some information. Some representation to present some information, that is called the representation. Okay. To be effective communication, to be effective in communication, a representation must meet at least the following condition. The form of representation must be perceivable in some way. The relationship between the form and the content must be shared by all parties. The relationship must be shared by all parties. Now what we see that, for example, we see this button, we see in our mobile phone these buttons. What does this button means? We see many places these kind of buttons. It means run. Yumna, where did you see this as a run? Yes, in videos. So it means to run the video. This button. When you click this button, it will run the video. To run the videos. Okay. Fine. This button is to run the video. How did you come to know that this button is to run the video? We have seen this, we used it, okay, and we have seen many times, 100 times might be we press this button, more than 100 times, 1000 times might be we press this button to run a video, to play a video, or to run an audio, to run a program. Even if you see in some programming languages, I'll show you here, this button, it means run the program, run the software. Okay, so here the representation of particular symbol, this symbol says running or playing. This symbol says running or playing. You can see here this run button. We'll take you this one here. You see this button here? This is run button. Fine. And this is clock button. So you see that we see in different places some symbols that has a meaning. But if you see some buttons that has no meaning, how do you feel that? I would ask you, for example, let's say that on the road there is something like this. On the road. What does it mean? Nothing. We don't know this. What does it means? With the green, we don't know. With the red, we know. With the red, we know that no stop, no horn. Okay. Don't come. Might be. Fine. So we see that every symbol has a meaning, and that symbol can be used to represent something. Can be used to represent something. Now what does this mean? Korea. What does this mean? Yeah, 7. 7 in Arabic, or letter V, or what? Or 6, not 6, 5. Number 5 in Roman. So this can be 7 in Arabic. This can be what? This can be number 5 in Roman. This can be letter V in English letters. This can be a winning symbol at the playground. So the symbol has meaning, and this meaning to be shared. If I am using this in Arabic context, this means 7. If I am using this in Roman context, this means 5. If I am using this in English, like I am writing heaven, for example. So this V comes here, it is in letter V. When I am writing like this, when it comes in Arabic, it says, okay, it is 7. When I am writing like this, it means it is number 5. Fine. So symbol will have the meaning. We need to say that every symbol must have a perceivable meaning. We should know the meaning, and we should know that all parties in communication must be exchanged, must know this meaning for every symbol. Okay. So a human may have different way of perceiving the representation, taking the representation, which is all used in our communication with computers. We have the auditory representation as perceived as sound. Human can perceive the information, can communicate by listening. While I am speaking to you, you are typing me something, right? So I am using an auditory representation to explain you something, and you are writing me something that I am using my visual representation to see what you are writing. To see what you are writing. So in auditory representation, it can be spoken languages or music and alarms. In visual representation, you can see the signs, traffic signs, flags, paintings, text, images, and all. Tactile representation, which is perceived by touch, by touching it. Let's say, for example, you have a cup of coffee. If someone asks you whether this coffee is hot or cold, very simple, you go and touch it. You perceive the information, you take the information. You say, sir, this is hot coffee. Or if it is cold, you say, sir, it is cold coffee. Fine. So different things, even the vibration in your mobile phone vibrates. This means that something is happening in your mobile phone. Something is happening in your mobile phone. Fine. So a human perceives the information or representation auditory, visual, and tactile. Almost any analog quantity can be represented digitally. Any analog thing can be represented digitally. This means that the representation can be stored and manipulated by computer, because computer store only digital things. Okay, so this means that we can convert almost every analog property into the digital form, which means that we can store them, we can manipulate them. So we'll discuss now how the digital codes are used to represent the images and the sounds. Whenever you take a photo, use your mobile phone camera, you click a picture. So when you click a picture, the outside world scenery or the picture is now converted into a image, a digital image, and is stored in your mobile phone. So we will see that how that is happening. And we also see sound. When you record a sound, you open a recorder, record a sound, that sound will be recorded and it will be stored. So how this sound, which is an analog property, is converted into digital and is stored inside the computer. That we will see inshallah now. For an image, basically on computer, the images are generated by dividing the display into large number of tiny units called pixels. The whole image is divided into small units called pixels. Each pixel display a number of different colors and level of light intensities and brightness. The greater number of pixels for a given size of display, the more detail can be displayed and higher the quality of the image. So if the number of pixels is more, the quality will be good. If the number of pixels is less, the quality will not be good for an image. To begin with, let us consider a black and white image of the triangle, of this triangle, a black and white image. So we see that we look into this black and white image. Let us consider an artificial sparse scale example. A display using 8 row, 16 pixels triangle, as you see here, 8 rows and 16 columns. Fine, to represent a triangle here. Fine. So if you want to represent this triangle inside the computer, how do we represent is that we mark every white pixel, white, we mark them as 0, and every black we mark them as 1. Fine. So as you can see here in this part. Fine. So 1, wherever there is a 1, if you look into this, it forms a triangle. Fine. Every black is marked by 1, every white is marked by 0. So if you represent a white pixel by 0 and a black pixel by 1, then we can code the image and convert that into zeros and ones, binary numbers, and then we can store this inside the computer. By increasing the number of pixels, we can improve the amount of details in the image, get the high quality black and white image. If you increase the more number of pixels. This sort of encoding an image into the digital, we call it as an raster graphics or bitmap, where every pixel is converted into a number. Every pixel is converted into a number, we call it as a bitmap or raster graphics. If you want to use colored pictures, we can use color pictures by using the binary numbers, like for example 00 is white, 11 is black, 10 is blue, 01 is red, like this. So you can have, for example, if you want 8 colors, fine, this is only 4 colors you will get. When you have 2 to the power of 2, which is 4 colors. If you increase the number of bits, 2 bits, binary, 2 bits, 4 colors. If you get binary, 3 bits, then you will have 8 colors. If you get binary, 4 bits, you will have 16 colors. You will have 16 colors. If you want more, you need to increase the bits. You need to increase the number of bits. As the number of bits increases, the colors also increases. The number of colors also increases. Fine. So a set of given number of bits used to data representation is called binary word. Is a binary word. So n-bit binary word can represent 2 power n different options. For example, if you want to 300 colors, we need 9 bits word length. 300 colors. 8 bit is 256 you will get. If you want 9 bit, 2 power 9, which is almost 300. Any coding scheme allocates a binary code to each pixel in order to define its color brightness. Is called a bitmap image. So any coding scheme that allocates binary code to each pixel is called a bitmap or raster graphics. Bitmap or raster graphics. Okay. File formats are agreed upon standard ways of organizing and storing binary data that represents the image in your computer. You have different file formats. You have JPG, JPEG, BMP, the bitmap image. Okay, different file formats uses different way of representing the images. Because bitmap files are relatively large, they are not most appropriate choice for the format of the image to be viewed. Other techniques such as JPEG uses information about human perception to reduce the file size. They still assign a binary code to pixel, but in different ways, which is called bitmaps, which is not like bitmaps, which is called JPEG, Joint Picture Expert Group. Vector graphic, we have another technique, is a image coding technique. Instead of sending or storing information about each pixel, information about different shapes is stored. Information about different images or the shapes is stored. Vector graphics is most appropriate where the image is made up of several regular shapes, as in many web or component graphics. Example, a straight line can be defined by starting and ending points. A circle can be defined by its radius and center and the radius. So in vector graphics, what happens? Vector graphics, for example, if this is an image, let's say this is an image. So how the raster graphic will store what is the pixel number here, what is the pixel number, what is the pixel number here. Let's say this is 2, 3, this is 7, 4, this is let's say 7, 2. So it will store point numbers 2, 3, 7, 4, 7, 2. Fine, the pixel numbers, and it will draw the lines. And also for the line, start point and the end point. What is the start point and what is the end point is stored. Also for the circle, what is the center and the radius of the circle. If you know this center and the radius, you can draw the circle. So this way of storing the images, we call it as in vector graphics. Vector graphics. So in this way, file size can be kept much smaller than bitmap, provided a complete graphic contains only of the shape allowed within the vector graphic system. It is also easy to produce simple animation of such shapes for images such as photographs or motion pictures. The vector graphics is not effective. If you are taking photos in your mobile phone, videos, vector graphics is not good. Vector graphics is good only when you have the images with shapes like circle, triangle, rectangle, lines. Fine. The next real world implication. Computer memory and hardware we store these images. Computer memory where we store these images is measured in bits, bytes, kilobytes, megabytes, gigabytes. We all know about this. That what is the computer memory unit? It is bits, then bytes, then kilobytes, megabytes, and then gigabytes, then terabytes. Then terabytes. Right. So 1 byte is equal to 8 bits. We all know that bits are nothing but 0 and 1. Bit is 0 and 1. 1 byte of memory, it means 8 bits. It means it can store 8 zeros and ones. 1 kilobyte, it means 1024 bytes. 1 kilobyte, it means 1024 or 2 power 10 bytes. 1 megabyte is nothing but 2 power 20 or 1024 kilobytes. And 1 gigabyte is nothing but 1024 megabytes. Every time you go from bytes to kilobytes, 1024. Multiply by 1024. Now let's take a question here. A smartphone has a screen resolution of 640 by 960. It means 640 by 960 pixels on a smartphone. How much data in bits, byte and megabyte is required to display an image if it is using 16 bits for each pixels? First we calculate how many pixels. How many pixels we have? 640 by 960 pixels. So you calculate what is 640 by 960. 640 multiplied by 960. It is 614 400. Okay. Yeah. So 640 by 960 is 640 400. This is number of pixels on the screen. On the screen. This is your mobile phone and this is the screen. What is the number of pixels you have? You have 640 by 960 pixels. Okay. So it is total number of pixels is 614 400. The next is if it is uses 16 bits for each pixel, and 1 pixel 16 bits. Fine. How much data is required to display an image? For one image on the screen, what is the data required in bits, bytes and megabyte? So now it is using 16 bits per pixel. One pixel is how much? It says 16 bits. So 640 400 pixels. How much bits? You need to multiply by 16, which is multiply by 16, which is 9 830 400. 9 830 400 bits. This is in bits. Yeah. Now if you want to convert this bits into bytes, how many bytes it is? How do we convert bits to bytes? How to convert bits to bytes? Divide by 8, because 1 byte is equal to 8 bits. 1 byte is 8 bits. So we are going to divide this number by 8. We have 1 228 800. 1 228 800 bytes. And if you want to convert these bytes into kilobytes, how many kilobytes it is? How many kilobytes it is? How much? How to convert byte into kilobyte? How to convert byte into kilobyte? Divide by 1024. So we divide this again in by 1024, which is 1200 kilobytes. So it is 1200 kilobytes. If you want to convert this into megabytes, how much it is? Again divide by 1024. It is 1.17 megabytes. Fine, 1.17 megabytes. So this is how we can convert one memory into another memory based on their values. So the question was here is that if we have a smartphone with this resolution, how much bytes we need to store an image or to display an image using, if it is 16 bits per pixel. Fine. So you need to understand the conversions also, that 1 bit is 8 bytes. It is 1 bit, sorry, 1 byte, 1 bit is 0 or 1. 1 byte is 8 bits. So if you have bits and you want to convert to byte, you need to divide by 8. Divide by 8. And 1 kilobyte, we write kilobyte is 1024 bytes. So you need to divide by 1024. If you want to convert the byte into kilobyte, divide by 1024. And you have kilobyte to megabyte, it is 1024 kilobyte. So you need to divide this by 1024 to convert them into megabyte. Again, from megabyte to gigabyte, you need to divide this again 1024 megabyte. Fine, divide it. So you will get the gigabyte. So divide this by 1024, you will get the gigabyte. So this is a simple example. Another question here, consider an image size of 100 by 240. How many bits and bytes are required to store the image inside the computer? Using only two colors, using 3 bits per pixel, and using RGB model. RGB is nothing but red, green, blue model. RGB uses 3 bytes of data, 3 bytes. Okay, R 1 byte, G 1 byte, and B 1 byte. 3 bytes. 3 byte is how many bits? 3 bytes is how many bits? Someone tell us. 21, 24, 24, because 3 into 8, because 1 byte is 8 bits, 3 into 8 is 24. 24. So if I are using two colors, black and white, so it is only 1 bit is required. The size is 1024. Sorry, 100 by 240. It is 24,000. If you are using only two colors, black and white, it means only 1 bit is required, one for black or white. So it is only 2400 bits. If you are going to convert in bytes, it is 3000 bytes. If you are using 3 bits per pixel, we need to multiply by 3, which is 7200 bits. And you divide by 8, 9000 bytes. And RGB model uses 24 bits. 24 multiplied by 2400, 24,000, it is 576,000. Divide by 8, you will get 7200 bytes. Fine. This kind of problem you may get in the exam. Let's say that a file is 3 megabytes in size. How long it will take to download the file from the internet connection with a speed of 14.1 megabits per second. First, we convert this file size into bits because we are speed in bits, right? So we need to convert this into bits. That is 3 into 1024 kilobyte, 1024 byte, and 8 bits. So we multiply them to get the bits, and we get the seconds. Megabit seconds, we get only the second by multiplying 1000 and 1000 twice. Now time it is nothing but size divided by the speed. So we divide the size by speed, we get 1.78 seconds. So it takes 1.78 seconds to download what? A 3 MB image file. A 3 megabyte image file. To download we need 1.78 seconds. See, these are the problems that you may receive in the exam. A common bitmap format for displaying, this is another question. A common bitmap format for displaying a reasonable high quality digital image uses 24 bits per pixel. 24 bits per pixel. How many pixels are required for 1024 screen resolution? 1024 by 768 pixels required, which is 786 432 pixels. How many bits of data does this require for each image? So if you are using 24 bits, it means multiply the number of pixels with the size 24. You will get the number of bits. My internet connection is 2.3 megabits per second. How long it will take to upload such file? 2.3 megabits is nothing but 300,000 bits. The size, okay, and the speed is 2.3 megabits. Sorry, size divided by speed. The size is, what is the size? Size is this 188, 743, 68. Divided by the speed will give you the time. Divided by the speed will give you the time. Okay. So that's about representing the images and some questions on images, on memory and the images. It is important to understand this because you may get a question in the exam. The next we talk about representing videos. Representing videos. Videos are not same as images, as we all know that, right? There is a question using 1000 or 1024. See, there are two things here. If you are talking about memory size, it is 1024. If you are talking about speed, it is 1000. Clear? We said here for 2.3 megabits per second. What does it mean? We are talking about speed or memory? We are talking about speed. When it comes to speed, if you want to convert kilo it means 1000. Mega it means 1000, 1000, and multiply them. Right? That is the speed. Okay? You have meter, centimeter, meter, kilometer, megameter. Right? So here when it comes to speed, we go by 1000, multiplying by 1000. When it comes to memory, like it says 1024 by 768 pixels, how many bits are required to store them when you are using 24 bits per second? This is talking about memory. So it is this one, bits. If you want to convert this memory into megabyte, kilobyte, gigabyte, you divide by 1024. So first you divide by 8 to convert to byte, then divide by 1024 to convert to kilobyte, then divide by 1024 to convert to megabyte. Okay, is it clear? Fine. Is it clear to you? Okay. Representing videos are not same as like images. A video or a movie is a series of images that slightly differ from one another. Passing them at a certain speed will illustrate you like a movie or a movement. Frame rate is a speed of flipping the frames one after the other. Frame rate is nothing but skipping the skipping the frames one after the other, or flipping the frames one after the other to make the video. That is called the frame rate. Now, films are usually shot and displayed at 24 frames per second. It means that there are 24 images in 1 second video. If you play 1 second video, you will get 24 images. In that, there will be 24 images. In that, there will be 24 images. 1 second, please. Now it says like films are usually shot and displayed at 24 frames in 1 second. TV pictures are presented between 25 to 30 frames depending on the what we country it is. In Japan, it uses not as 60 frames per second. That is the HD TV. What we call the HD TV can flip 60 frames in 1 second. It means that there are 60 images to display 1 second of movie. 60 images are used to display 1 second of movie. That is the frame rate. Now let's say question here. Let's say that we have a 2-hour film to be displayed on a computer at 24 frames per second. 2-hour film, right? And displayed, the film is played 2 hours. The film is 2 hours and displayed at 24 frames per second. Displayed at 24 frames per second. 2 hours is how many seconds? 2 multiplied by 60 minutes multiplied by 60 seconds. Fine, which is 7200 seconds. 7200 seconds. Fine. Okay. Now it says each frame is 640 by 380 pixels. One frame. So one frame is how much? 640 by 380 pixels, which is 640 by 380. 24 3200. 24 3200 pixels in one frame. In one frame. Now, and a 24-bit RGB color encoding is used. It means that we are using 3 bytes. 24 bits, it means 3 bytes. 3 bytes for every pixel. For every pixel. So if you are having frame size this 24, 3200 and every pixel in the frame is 3 bytes, then you have 24, 3200 by 3, 72, 9600 for one frame in bytes. Byte for one frame. One frame is 7296. Now you have 7200 second, 24 frames per second. How many frames you have? 7200 seconds, 24 frames. It will be 172 800 frames. 24 frames in 1 second. How many seconds? 7200 seconds. So you will be having 172 800 total frames. What is the frame size? This is in bytes. So you multiply 72 9600 by 172 800 size of one frame by number of frames. Number of frames. You will get this number, which is 117.416 gigabyte. 117. So we will convert this 172 9600. If you talk about this 72 9600 multiply by 172 800. 172 800. So it is no 72 9600. Oh, sorry, I did wrong here. 72 9600 multiplied by 172 800. 172 800. So it is, this is number of bytes. Number of bytes. You convert into kilobyte, divide by 1024. This is kilobytes. Again divide by 1024. This is megabytes. Again divide by 1024. This is gigabyte. So we have 117.41 gigabyte of memory to display to our film. To see to our film or to store to our film, we need 117.416. Is that true? I think you have seen the size of one movie of 2 hours. What is basically the size of one movie of 2 hours or 3 hours, whatever it is? I think you have seen in CDs, if you talk about the movie inside a CD or in a flash memory, what is the maximum it can take memory? 3 GB? I don't think so it will take 3 GB for 2 hours. I think it is only 700 megabytes or maximum 1 GB. Right? But you see here for 2-hour movie, according to our calculations, it is 117.416. 117.416. What does it mean now? It means that we cannot store this in a CD or in a flash memory. We need a hard disk to store this one movie. So if your hard disk is 500 GB, you can store only 4 movies. Is it that true? And if your hard disk is 500 GB, you can store only 4 movies. Is that true in reality? That you can store only 5 movies or 4 movies? Yes, students. Is that true that you can store only these small size, big size, 4 movies in your laptop or in your hard disk? No, it is not. Right? Then what we need is we need a compression. We need compression. We need to compress this. Fine? We need to compress it. We need to reduce the size. So we'll talk about compressions later. That's about the movie. Now coming to the sound. The sound, how we can record a sound. Till now what we talk about the images. Images can be represented as a movie. But what about the sound? So Audacity is a sound editing program to record and manipulate sound, which is you can see here. Audacity. It is available in computers using Windows and Macintosh operating system. The program allows you to load, record and save and play the sound using different file formats. What you can see here. Okay. Now sound is an analog feature that we want to convert that into the digital. Okay. Sound, what we hear, generally consists of rapid movements at the atmospheric air pressure. The rapid movements at the atmospheric air pressure. So for example, if a person, let's say that a person is speaking here. Fine. When a person speaks from here, from the mouth, what happens is that the air here around this will be shaking, moving. That's what it is. A small rapid movement of atmospheric air pressure that surround us is the sound. Whenever we speak, for a person speak from his mouth, fine, speak from his mouth, the air here, what you call in Arabic hawa, the air here will fluctuate. The fluctuation of the air is what the sound is. For example, vibrating a tuning fork will make a sound. For example, if you have a tuning fork like this, you hit this here, it will generate a sound. Even you hit a table like this, you can hear a sound, right? Even you hit a table, you hit a paper, or you flip the paper, you can see you can listen the sound. Now what is happening is the air around this, the air around it will be fluctuated, goes up and down, fine, that makes the sound. We can write it like a waveform, as you can see in this one. So like when we are speaking from here, so the air here goes up and down, up and down, up and down, that makes the sound. That is what the sound is. Okay, that is what the sound is. Now a cycle represents the time between the adjacent peak and the number of cycles completed in a fixed time is known as a frequency. So this is a time cycle, it goes down and reaches to the same level. This becomes one cycle. And how many cycles are there? That is the frequency of the sound. So if we have, for example, here, it goes to here till here, 1 cycle, 2 cycles, 3 cycles, 4 cycles. So frequency is 4 here. Okay. The amplitude of the wave determines how loud the sound is. The length, you see this from here to here. This determines what is the sound loudness, high or low, is determined by this amplitude. Right? The frequency decides the low or high pitches that notes the sound to us. In this figure, we see the sound as a wave increasing over the time. So a tuning fork is very simple instrument that so make a pure sound. Real instruments, real noise are much more complicated than this. An instrument like clarinet would be a complex waveform. A dropped plate will have irregular forms. Fine. So, for example, an instrument like clarinet will generate the sounds like this. Fine, as you see here. Whereas a dropped plate may generate a sound like this. So, different sounds, will generate a different fluctuations in the air, different waveform, different sound. For example, if I hit the table, this is something different sound. it will create something different wave. And if I do this paper like this, if I shake the paper, this makes another sound. This will have different waves. Fine. So different sounds, different waves. But the question here is how to convert the sound into a digital form, because we want to store the sound in a digital form. And you see that there is an audio file. Audio file, it means sound. Sound is stored inside the computer. How to store them? In a form of digital. We need to store it as digital. But how to make that as digital? That is the question here. How to make it as digital? So for example, a microphone is used to convert the sound pressure wave into the analog electrical signals. Now here comes the microphone. So here comes the microphone. I think we all have seen the microphones. Excuse me. Okay, a microphone is used to convert the sound pressure waves into an analog electrical signals. But so microphone, I think you have used the microphone. You are using microphones, So what happens is the microphone is used here to convert the sound pressures, the pressure around the microphone into electrical signal. These electrical signals need to be converted into digital. So process of converting the sound include two stages. There are two stages, that is sampling and quantization. Sampling and quantization. You may get this in the exam. What are the two steps or two stages of converting analog into digital? So two stages is sampling and quantization. So as we split up image by dividing them into pixels, we can split a sound by dividing into very small time intervals called samples. In image, what we did, we divide the image into pixels. Like if we have an image like this, we divide them into rows and columns. That is called pixels. Even in sound, we can divide the wave. For example, if this is a sound wave, we can divide it by taking intervals, samples at regular intervals. For example, we'll take it one here, one here, one here, one here, one sample here, one sample here, one sample here, like this. Right? So it is dividing into very small time intervals called samples. The first stage of the process is to measure the amplitude of the sound at a regular time intervals. Taking the reading like this is called sampling. So we are taking the samples from the wave. Taking samples from the wave at regular interval, which is called sampling. The number of times you take the samples in 1 second, we call it as a sampling rate. In 1 second, you take how many samples? 10 samples, 20 samples, 100 samples. That is called the sampling rate. You can see in this figure now, on every 5 second, every 0.5 second, we are taking samples of the wave. Every 0.5 second. So we'll take the 0.5 second. What is the sampling? What is the sample we take? The amplitude is this one, which is, let's say, 9.3. Next 1 second, we take the next sample, which is minus 3.1. Next, we take the sample at 1.5, which is minus 4.1. Next, we take the sample at 2.0, which is 8.2, plus 8.2. Next sample 2.5, it is minus 10.0. Next sample 3.0, it is 4.0, 4.5 at 3.5. So you see, these are the samples what we have taken from this figure. So what is the the interval here, it is 0.5 second. Every 0.5 second we are taking the sample. How many samples in 1 second? 2 samples in 1 second. That is, the sampling rate is 2. Sampling rate is 2 because we are taking only 2 samples in 1 second. Fine. Now, if you take these 2 samples in 1 second, according to these numbers, according to these samples, if you plot the graph again, at 0.5 second it is 9.3. So at 0.5 it is here 9.3. Then at 1 it is here. At 1.5 it is minus 1.4. At So if you put these samples back again, at 0.5 it is this 9.3 plus at 1 it is 3 at 1.5 it is minus 4.1. This is at 2 it is 8.2 here. At 2.5 it is minus 10. At 3 it is here plus 4 plus 4.5 at 3.5. If you draw the graph like this, so you will start from here. Okay, how can you draw the graph digitally? It will go like this. What you see here is this way. Is this graph is equal to this graph? Is this is equal to this? Are both same? Are they both same? And students online, are they both same? Are you sure they are the same? You can see the graph this one, how it is. And you can see the graph this one. You see the graph is here. We have the graph here, but here we don't have that. They are not same. Okay, they are not same. So if you plot the new graph from the waveform, we just get this number, we get this graph. So the plateaus at every sample point represent the interval between samples where we have no information. So assume that nothing happens. This means that the audio signal produced by the sample does not follow the original signal. It means this sound is not equal to this sound. They are not equal. So you will get a poor quality sound. Why? Because you are taking only 2 samples in 1 second. What we have to do is we need to increase the number of samples. To improve the sound quality, we have to increase the number of samples. So let's say that we take the same image and we take the samples at 0.1 second. So it means in 1 second 10 samples. Sampling rate 10. So if you talk about this one and you plot this graph again with what the samples is taken, this looks very similar now. These two looks very similar. Hence you can get a good quality sound. So to increase the sound quality, what we have to increase? We have to increase the sampling rate. To increase the sound quality, we have to increase the sampling rate. Fine. To increase the picture quality, the image quality, we need to increase the pixels. We need to increase the number of pixels. And to increase the sound quality, we need to increase the number of samples of the sound. Okay. Now the next process, this is sampling. The next process is quantization. In the second stage, it is the process of converting each sample into a number which can be stored inside the computer. Fine. So every sample is now converted into numbers, divided and converted into binary numbers, as you can see here. Fine. So and these numbers are stored in the memory, as you can see this here. Fine. So which are stored in the memory. Hence, this is the sound what is inside your computer. when you play the sound, these numbers are converted into the waves and the sound will be played. So if we want to just send sound somewhere, then we can just simply send these numbers. We are sending these numbers. Fine. So any device that can store large quantity of numbers can be used to store the sound, such as the memory, the phone memory, the hard disk, the CD, the flash memory, and all. That is to store the sound. So this is how the conversion of sound to digital form happens. So it is the waves are converted into, we take the samples of the waves and those samples are converted into numbers and those numbers are stored and those numbers are shared. Fine. Now let's take a question here. For a 4-second single channel storage, suppose that each sound sample requires 2 bytes of storage and every sample 2 bytes of storage. That has an additional 44 bytes are needed for the format of the sound. If the sampling rate is 44,100 samples per second, what is the size of the file? And how many samples in 1 second? 44,100 samples. And one sample is 2 bytes. One sample is 2 bytes. So now the sampling rate is in 1 second. How many seconds we take the video? How many seconds we record? We record for 4 seconds. 4 into 44, 100. Number of samples in 1 second is 176, 400. Every sample needs 2 bytes. Multiply this by 2. Plus it needs 44 bytes for additional information. So this is the number of bytes required to store a 4-second audio. That is 35, 28, 44. 4-second audio needs this size. Okay. But still it is also a big number. You can test this. We have this 35, 28, 44 bytes for 4-second audio, which is, if you divide it, 3344 kilobytes divided by 1024.33 megabytes. Is it true that you have 4-second audio with this size? 4-second audio comes in bytes, 1 byte, 2 byte, 10 bytes maximum, right? So now we see that basically when we saw the representation of images, representation of video and the sound, we see that it needs a big memory. For the image, for the video, we saw here that it needs 117 for 2-hour movie, which is not correct, which is not good yet. For an audio, we see here 35, 28, 44 bytes only for 4-second audio. If you talk about 2-hour audio, it will be in hundreds of GBs. Fine. So what we will do here is we are going to compress the file. So we talk about compression here, compression of digital files. The digital encoding sound and images in videos are large data files. For example, 500 pages of a text document in a plain text format can be take 1.8 megabytes. 30-second video can take 186 megabytes. Compression here, it means that reducing the size of the file, that is original digital file, and taking the original file and converting it to a new file that is considerably less in memory. The ratio between the compressed file and the uncompressed file can be given by the size of the compressed file divided by the size of the uncompressed file divided by size of the compressed file. The ratio can be given like this. The higher the compression ratio is, less storage space would need to for the resulting compressed file. If 10 megabyte file is compressed to 2 megabytes, the ratio is 10 is to 2, which is 5 is to 1, which means that any 5 megabyte file can be converted into 1 megabyte. Okay. We have basically two types of compression: lossless compression and lossy compression. Two types of compression: lossless compressions and lossy compression. Lossless compression technique, where you do not lose any aspect of the original data. You don't lose original data. That is the lossless compression. Lossy compression is where you lose some data, but in a controlled way. You don't feel that you lost something in lossy compression. Decompression is the reverse of the compression. You compress the file and you uncompress it or decompress it. Bring them into original form, what is called decompression. Okay. Now let's talk about lossless compression and lossy compression. Fine. Lossless compression and lossy compression. Before we talk about this, is everything clear to you all? Students online, everything clear to all? Okay. Talking about lossless compression, the digital data stored in a compressed form can be recovered as it is. As it is. For example, zip file. I know you have. I think you have used this zip file. Fine. Where zip file is lossless compression. When you compress any file into a zip file and you decompress it, you will get the same original exact data. You don't lose anything. That is the zip file. A powerful form of lossless coding is dictionary-based coding. Lossless coding is dictionary-based coding. How the compression is taken. In most digital files, some data is repeated over and over again in digital files. In digital file, a compression algorithm simply get rid of this repeated data or repeated patterns. How it is, for example, if you look at this statement, when the going gets tough, the tough get going, right? So according to this dictionary based coding, what will happen is every word is given a number. It will create a dictionary, like every word will get a number. For example, 1 it means the or the, 2 it means going, 3 it means tough. Okay, so we can, the going tough are repeated here. Going is repeated 2 times, tough is repeated 2 times, the is repeated 2 times. So anything repeated, what we will do is we are gonna assign a number to it by creating a dictionary. Now we can write the same sentence like this: when 1 2 gets 3, 1 3 get 2. Right? Now you count how many letters are there in this. There are 9 words, 8 spaces, 2 punctuations, a total of 48 characters in this sentence. The same sentence, we use the dictionary and we write it again. Now this sentence has only 27 characters. So we reduce from 47 to 27. It's almost like 50%. We reduced. 2 is to 1. Compression here is 2 is to 1. The ratio compression is 2 is to 1. Right? So we reduce it by dictionary. This is what the dictionary based coding is. So in dictionary based coding, we look into the repeated words, the repeated data, duplicated data, create a dictionary of it, okay, and rewrite the sentence by using this dictionary. you may get a question in the exam. They'll give the sentence and ask you to compress it by using dictionary based coding. Compress it by using dictionary based coding. So what you have to do is you have to select the repeated words. What are the repeated words? Okay, and for those repeated words you have to use what? The numbers in the statement. Fine. Fine. Is this okay? Is it clear? Dictionary based coding. Is it clear to all? Dictionary based coding. Yeah, it is the same as zip file or WinRAR. These are all lossless compression. Another technique for lossless compression is run length encoding. Run length encoding. In this compression method, runs of similar data items are recognized and replaced with a single instance of data item, together with a number indicating how many times it repeats or the item is repeated. For example, let's say that the strip pattern in figure 17 can be represented by binary sequence 0101. The repeat of 0101 7 times, this can be represented as a run length code of 7 of 01. So if you take this one, if you want to compress this one, let's say that it is 0 and this is 1. So how many zeros and ones? 1, 2, 3, 4, 5, 6, 7. So 7 times 0, 1. 0 means what? White, 1 means black. That means first white, then black, then white, then black 7 times. This type of coding we call it as a run length encoding. Run length encoding. Now here also you can see that in this figure also the run length encoding. So let's say that it is the run length is 111111 for black and 000 for white. So first how many 80 ones we have? How many ones? 81. Then 28 zeros, then 21. So what we will write? 80 of ones, 28 of 0, 20 of 1. So you can see the whole image is now this number. Okay, so lossless coding is used in a similar way for simple images such as line drawing and simpler shape graphic GIF images. Okay, website images and all. This is a simple way to store by using run length encoding. In lossy compression, the original file size is processed in a way that preserve the important information but discard other information which is less important. Like for example JPEG images. These are all lossy compression techniques. In lossy compression techniques, we lose some data but in a more systematic way so that we don't feel like what we lost. Right? So lossy compression is another compression technique where we gonna lose some data when comparing data or compressing the data. Fine. So we will stop here for today. For today we will stop here in lossy compression. Or let's take the lossy compression and we will start at the number system. Okay. Lossy compression of audio. 1 minute please. Lossy compression of audio, image and video files exploit features of human perception to reduce the amount of data needed. Psychoacoustics is a study of how humans perceive and respond to the sound. So humans may not look into the minute details or very minute details, we don't perceive them. For example, sound, some minute sound we don't perceive them, right? So in this lossy compression, those sounds which humans don't feel, don't perceive, will be taken out, will be will be deleted from the original data without affecting the quality of the sound, or without affecting the what to be perceived, right? That is in lossy compression. Digital image compression, as described before, digital image is made up of multiple elements, that is pixels. So more pixels there, the higher is the resolution, but greater it takes the memory. So there are two solutions to reduce the image size: reduce the number of pixels or compress by using some compression technique. So we can use like JPEG or MPEG video, audio, and sorry, video and image compression to remove the repeated components or the not important components from the images and from the videos, to compress the file, to compress the images. So we see that the images are more compressed when it is JPEG format, because it is a compression technique, and lossy compression technique where the unwanted data is removed from the images. Okay, so this is all about the compression. So basically in compression you have two forms: lossless compression and lossy compression. Okay, these are important things you have for your final exam. So today we will stop here for today, and inshallah in our next meeting we will continue from the number systems. Okay, do you have any questions, students online? Any questions? Okay, let me take your attendance before we leave.